name is Jeppe Bjerring, and I am from Hewlett-Packard. I have to start learning to say Hewlett-Packard now, not HP anymore. I am the business manager of high-performance computing in the Nordic region, which also in our terms covers the Baltics. So I'm very happy to be here. And I am very fond of Erwin's talk just about an hour ago, because I am going to try and talk about some of the same topics. But of course, I am from the industry, so I will talk about how we try to solve the same problems that Erwin is talking about from the academic or the scientific world. And before we start, have you ever heard about HP Moonshot? Do you know what HP Moonshot is? You heard that we have a product called HP Moonshot. If you haven't, it's a project that launched a couple of years ago, and today it's a productized product. We sell this product to our customers, but I will try and put it in a larger context and show you how it's a stepping stone to what we believe will be the design of the future computer, and how we will help solve the exascale problems or the exascale challenge that we have. But I'm going to start somewhere else. I'm going to start with my iPhone, because my iPhone and all you guys, everybody has a smartphone, right? So everybody knows that smartphones have taken over the mobile communication, and mobility is probably the biggest new trend that we've seen. The fact is that, and when we look at development, and we look at what's going on and how many chips are being manufactured in the world, today the chip manufacturers are making more chips for smartphones than they are for computers. So these devices are now the forefront of the development of digital products, right? And the biggest challenge with these devices, it's not necessarily the speed of the CPU or the memory. It's one thing. It's the power consumption. It's the power. I mean, when we had our Nokia phones 5 or 10 years ago, they would last for a week. We wouldn't have to charge them until 8 or 10 days were gone. Now I have to charge this 2 times a day, because I'm using it for my email, for Facebook, for everything. So when Apple was developing the iPhone, they were actually, well, the rumor has it, they were actually pretty much ready quite a long time before they launched it. They only had one problem. It wouldn't last a full day, because the batteries were bad, but also because the programming, because the code that they were running were not really optimized for the kind of CPUs, for the kind of chipsets that were in the smartphones. So it comes down to the same challenge that Erwin was talking about earlier this morning, that power is the biggest challenge. So Moonshot is trying to tackle that. Our Moonshot servers are low-powered servers. They're ARM processors that we're using. We're using 12 watts per core. We're not using 145 like Intel is using. That's what we're trying to solve. And what I'm going to show you today is how we're going to put that in a larger context, and I'm going to show you why it could be the way to solve the equations that we have. Right, so we're going to start somewhere else. We're going to start with this guy. And I came to think about this yesterday, because this guy is called Martin Fink, and he's the Chief Technology Officer in HP, and he's the director of an organization within HP that we call HP Labs. And exactly a year ago today, he was on stage in Las Vegas at the biggest customer event that we have in the world. It's called HP Discover. It's an annual event. And he was giving the keynote. And the speech he was giving was called The Machine. And the machine is, well, it's basically what he's holding in his hand, because the machine is HP's answer to the computational challenges that we will see. So in the labs and in HP, we've come to the realization that the way we design computers, well, it hasn't really changed a lot since the 70s. We've been doing it the same way for the last 30 or 40 years. So perhaps it's time to change the way that we design computers. Perhaps it's time to make a radical change in the way we do the hardware design. And that's what this speech was about, the machine speech. So these are the kind of things that we're trying to solve. And so the magnitude of data, the data is exploding. I'm not the first guy saying this today, but the amount of data is really exploding. And the way that the biggest issue with the data is the magnitude of it, and the fact that 70% of all data will never get moved from the place to which it's written in the first place. mainly because it's so big, because it's important. It's impossible to move the data around. When we look at all of the things that's creating all this data, they will be flash flooding all of the databases. And we see that we've got a lot of machine data coming in. We're putting sensors into everything, into airplanes. We're putting sensors into computers. We're putting sensors everywhere. And all of these sensors, they are generating tons and millions of terabytes, petabytes, and zettabytes of data. And they will be flooding our traditional databases. There's another problem with all the data, and that's we need to secure it. We need to make sure that this data is secure. Everybody knows not everybody is friendly guys on the internet, so we need to make sure that we can secure the data that we have. And if you're an enterprise, you make sure that you want to protect your intellectual properties. If you're a research institute, I'm sure you want to protect your research results. So security is going to be a big issue, particularly when the data growth is exploding as we're seeing. And it's time consuming to do all the data integration. It really is time consuming. But what we really need is, so the real dilemma is that because it's so time consuming, and what we actually want is real-time insights. So we don't want to waste, or we don't want to, here's your data, and then 14 days later you will get the results. You actually want the results right now. So you want to know exactly today, right now, what's happening in my airplanes, what's happening with all the things that are generating the data. And basically we do have insufficient resources. We do not have enough power. We do not have enough memory bandwidth. We do not have enough network bandwidth. So that's the thing that the machine is going to try and resolve. So what is the machine? Well, right now it's an idea. It's an idea of a way to redesign the server, redesign the computer. It basically has three components. And on which is your right-hand side, there's a massive memory pool. A massive memory pool is, think of it as, well, what we have today is not massive memory pools. It's individual pools of memory, because you've got memory in each server, right? Each server has its own memory. But that's really not quite clever, because what if you're wasting a lot of memory sitting in a single server, but you're not able to address it from another server? So a massive memory pool will be, think of your data center and think of all the memory that you've put into your data center being accessible to one single server. So all the memory you've ever bought, all the memory in your universities, being pooled into one resource pool and being addressable by all the computational resources that you have. That's a massive memory pool. So that's a shared pool of memory. And it's going to be persistent memory that's going to change the world, the way that we're looking at storage today. You will be able to have persistent memory, and NVRAM, or whatever we will be calling it. Memory technologies coming out as well, already available today. That's going to be the kind of technologies that we will see. Massive memory pools means that we need some kind of way of interconnecting the memory across the data centers. And that's what we're developing right now. And what we're working with is a light technology called photonics. And the photonics is a way of ultra high-speed interconnects that will make it possible to address memory right across the data centers. And on the other side, we have these special purpose cores. So the kind of cores that we have today, they're general purpose cores. I mean, when you take a standard CPU from Intel, it can do all sorts of things. And basically, you have to compensate when you're writing your code. You have to compensate for the fact that it's a general purpose system. What if you could get a system or a chipset that was actually a special purpose, and when you wrote your applications, you wrote it to a special purpose core instead of a general purpose core? Then suddenly you might be able to gain even more benefits from the fact that you have. So this is the idea behind the machine. So all of these special purpose cores and all of these massive memory pools will be tied together by interconnected photonics, and it will completely change the way that we build computers and the way that we build servers in the future. So this was launched a year ago, and so you can see that there is a I mean, we don't have this computer right now. I can't sell you one tomorrow, even though I would like to. But this is what we laid out a year ago was a roadmap. And we laid out the tasks that we need to solve before we can go and sell these kind of systems. So at the very bottom, well, we do need an ultra-efficient hardware platform. That's given. And that's what we're really good at. At HP, we're really good at working together with our partners at Intel, at Texas Instruments, at ARM, at AMD, to make sure that we get ultra-efficient hardware. And this also goes for the memory, right? Because the memory bandwidth, we need to make sure that the memory bandwidth is capable of handling this. And then we need to put a specialized operating system on top of it. We're calling it the machine OS, but think of it as a stripped-down Linux kernel that's only there to make sure that the hardware is running. Nothing, no general purpose libraries or anything, just a stripped down Linux kernel that only does one thing, make sure that the hardware is running. On top of that, we need a way of managing this, because we need to make sure that this can scale to the exascale, to the exascale sizes and even further than that. So this is the new way of, and how do you manage millions or thousands of computational compute nodes in just one interface? That's the challenge. Then we need to make sure that we've got the exascale algorithms in place. And of course, we need to make sure that we can run analytics and then visualizations on top of this platform. So this is the way, this is the roadmap we've built. And we've gone even further. We've set out to say, okay, so where are we in terms of making progress? And where are we, and when will this be productized? So when you look at 2014, which was last year, we already started manufacturing SOCs. And an SOC is a system on a chip. And an iPhone is an SOC, it's a system on a chip. We'll get back to that in a second. And so HP started out this development program. And in 2014, we started selecting these partners that was going to be joining us in this journey of developing the machine. And we also started developing the machine OS. So come to 2015, we're now seeing that the memristors are actually becoming available. Or actually, let's call it the NVRAM technology is becoming available. You can buy NVRAM from third-party vendors like SanDisk today, and it's already in the market. And I visited HP Labs back in April, and we have the first, I'm not even going to call them beta types, I'm going to call them something else, prototypes before a prototype running in our labs. And it's running on the very latest memory technologies from SanDisk. So in 2016, you will be seeing that the memristor DIMMs or the NVRAM is going to be more generally available, and it will become the standard memory that you'll see in your servers. And 2017, I believe that the machine OS will probably enter a public beta. Machine OS is going to be an open source. It's going to be open source because HP strongly believes in the open source community, and we strongly believe that the operating system of this machine should be in the open source community. 2018, and this point it becomes, well, it's not written in stone that these dates are going to be there. But I do believe that in 2018, 2019, you will see the first commercially available systems that's going to look like the machine. It's going to be available and going to be able to do, and going to have massive memory pools, special cores, and photonics as the interconnect technology. And by 2020, we do believe that this is going to go mainstream and be the way that you solve the exascale equation and the exascale problems that we're facing. Okay, so that's really shortly. That's the machine. But there are a lot of things that go into the machine. And one of the things that we're going to dive into today is the SOCs, the system on a chip. And the Moonshot, that's a system on a chip. So the reason why I told you this story is that, well, Moonshot is a stepping stone. It's a part of the development that we are running to get to the machine. And And when IDC came out just this month, well, actually in May, came out and said, IDC, every year IDC publishes a HPC market update. They give a lot of inputs to what's going on in the marketplace, and they also give us a lot of information about who's doing what. And one of the things that they point out about HP is that we're driving the innovation of Moonshot. That's really good to hear that IDC, a company like IDC, going out and say, well, we think you're on the right way. This is the right path to go. So now we're getting to it. What is the HP Moonshot system? So it's a server, right? It's a chassis. It's a nice little box, and we're not calling these guys. We're not calling the SOCs. We're actually not calling them servers. We're calling them cartridges. And this chassis will hold 45 smartphones, or 45 iPhones, or 45 cartridges, is what it really is. And they're all stacked together into that little chassis. And these are system on a chips, and these are special purpose cores. And this is going to be a building block of the machine. So when you look inside this machine, you will see that we have several ways of creating these special cartridges and SOCs. And I will get back to a few of them in a second. And then I will share some benchmarks, results with you, so you can see that we're actually getting pretty close to the performance of the Xeon processors that we have from Intel today. But of course, you need to remember the fact that these guys, they will use somewhere between 12 and 45 watts. So if you need to get to the same performance as 120 watt, you need to put 4 of those in there. So suddenly you're putting a lot more cartridges in to get to the same performance, but the power consumption is much lower, and that is the key, because you remember the story about the Apple iPhones. Power consumption is our biggest problem. So what we have in the chassis is that we have internal switching technologies, and then we are able to take these cartridges. We have several cartridges available today. I put them into the chassis, and you can populate 15 plus 15 plus 15, and you can run 15 at a time, or you can put all 30 in or all 45 in, and the chassis will run. But you have to put at least 15 cartridges in to make the system run. Some cartridges are a single server on the card, so there's a single CPU on the cartridge, and others is a quad server or has 4 CPUs on one card, meaning that in this little chassis you will actually get to not 45 servers, you will actually get to 180 servers in this tiny box, which is just 4 U's high. So that is the density, and that's the power of the Moonshot technology. We also need to solve the networking, because suddenly there will be a lot of traffic going on inside these chassis. So we've built, it comes with built-in data fabrics, and we have 3 different ways of addressing the interconnects into the chassis. We can use the radial communication. We can use the proximal array or the to-do torus mesh to make sure that all the traffic and all the interconnects, all the cartridges are able to speak to each other at a really, really low latency, which is going to be absolute key for running these systems. So when we look at an SOC, this is your standard server motherboard, or your standard motherboard from a laptop. And we're all putting all of these processors, bridges, storage controllers, management logics, video and NICs. They're all put in separate locations at the motherboard. That's how you know it. That's when you look at it. When you look at my laptop, when you look at your servers, that's what they're going to look like, right? And they're all interconnected with on the system board. So the radical change that comes from the SOC server motherboard is that they're all put together, right? They're all put together into the same chip. So now suddenly we don't have 8 or 10 different chips that needs to communicate on the motherboard. We now have just one chip that holds all those features. So we have the processors, we have the management interface, and we have the NICs and the storage controllers all put into the same chip. That's the system on the motherboard, or the server on the motherboard. And you can put DSP cores in there, you can put GPU cores in there, you can put ARM cores, you can put any type of CPU core into a system on a chip. And you can put it into our cartridges, and you can put it into our chassis, and you can run these servers. So I'm going to show you 2 cartridges. This is one of them. It's a 45 watt Intel Xeon E3 1284. It's Haswell based. And I'm going to show you these 2, this cartridge and another one, and I'm going to show you some benchmark results that we've run in the labs that we have in Grenoble, showcasing the performance of these cartridges. You've got some memory slots. You've got some integrated NICs. You can put some local storage in there, and there is support for several Linux-based and Windows-based operating systems on this device. The M710, and the other device is called M350, and it actually has not 1 but 4 Atom cores, Intel Atom cores on the same cartridge. So it's basically 4 servers on 1 cartridge, giving you up to 180 servers in a single chassis. And again, specs are not so interesting. So what we're trying to achieve is we're trying to figure out how much performance can we get from these small systems on a chips, comparing it to the more classical approach of our standard DL360 servers. So what we took here is we've built 20 kilowatt 42U compute racks. So what we're going from the power side here, we're trying to figure out how much computational power will we get if we have 20 kilowatts available. So the really interesting is that we took the previous Ivy Bridge CPUs, we took the current Haswell CPUs, this is the second column, and we took our more classic approach to our high-performance compute clusters, which is the XL230 platform, also Haswell based, and then we benchmarked it against the Moonshots, the 2 cartridges that you've just seen. And the results are pretty impressive. And then we look at the M350, which was the system that has 4 servers on 1 chip, or 4 chips on 1 cartridge. We actually see that we're able to outperform both the platforms of the classic DL360s and also of the traditional new Haswell platforms. And we're using a lot less space, and we're using a lot less power. So when we're turning to the spec CPU and benchmark results, we're running the same benchmarks results. And we're putting this into a 30 kilowatt rack, and we're trying to figure out how much computational power can we get if we have got 20 kilowatts available. And again, the results are pretty impressive coming in and saying, if you've got 20 kilowatts, well, you should, 30 kilowatts, sorry, you actually get more for your kilowatts and more for your spending dollar if you're going the Moonshot direction. We've turned to, if we turn to the Linpack scores, we're doing Linpack scores, and we're benchmarking the M710 cartridge, and we get to an efficiency of 84.1 with the current setup that you're seeing on there with the turbo off, and with the turbo on, we're getting to 112.2. So that actually means that per core, this SoC outperforms the classic V2 or the classic Ivy Bridge processors from Intel. So CPU performance is important. Memory performance is equally important. And for that, we run the stream benchmark. And again, when the results come in, you see that the M710 cartridge actually offers a much higher memory bandwidth per core than the traditional Ivy Bridge solution does. Again, so we're not only solving the CPU, the performance per CPU, but we're also solving the memory bandwidth per core, which is equally important. So we turn to the a more classic HPC. We've done the benchmarking. Now we're looking at 4 different applications, HPC, classic HPC applications. So starting out with the fluent dynamics, the answers fluent dynamics application. And again, you see this, that we're benchmarking the SL250s, the classic blade server, with Ivy Bridge CPUs. And basically results come in, they show that we're pretty much on par with the results that we have seen on the classic Ivy Bridge servers. So, and the same goes for the CFX, the ANSYS CFX applications. Again, the SOC-based systems, when you're comparing, when you're putting enough watts in there, you're actually getting to the same performance results as you are on the current Xeon applications. The crash simulation, ESI PAM crash simulations, and we're actually getting to a slightly higher performance when we're running on the PAM crash. And the last result that I have is the WASP, the computational chemistry, the WASP application. And again, the results come in for the Anders CPU, and which is the one that is right here. It's completely globally on par with the results that we're seeing from the Xeon CPUs. So this is the research that we're doing. This is the way that we're working with these SOC and these Moonshot technologies. And it's an important stepping stone in the way to get to the Moonshot, to the machine platform. And if you're interested in getting to work with these kind of systems, HP has set up a lab in several places around the world, but in Europe it's in Grenoble. It's a discovery lab. We have lots of systems running, and it's basically a lab that allows customers like yourself and researchers to gain access to our systems without having to buy them, to try and see if you can port your applications to these Moonshot cartridges and start optimizing your code for running on low-powered CPUs. And if you find that this could be interesting, then get in contact with your local HP guys and talk to them and see if you can gain access. You will get remote access to the systems in Grenoble, or you can come visit our center down there and talk to our experts and start working on writing code that will run on lower powered CPUs, which could be the future of high performance computing and could be the answer for the exascale challenge.